So welcome to today's Astrobiology seminar. Today we have Kevin Zahnle, who's a civil servant, scientist at NASA Ames Research Center. He did his PhD in the, one of those eons, 1985 at the University of Michigan with Jim Walker was his PhD advisor. He wrote, you may be familiar with that from certain papers about the evolution of the Earth. And then he did a postdoc, first at Stanford, and then at Ames. And he loved Ames so much that he's stayed ever since 1988, when he was appointed. And he works on impacts, atmospheric escape, planetary science, small bodies, comets. And as a result of his work, he's a fellow of the American Geophysical Union. He won some medal in 1996 for exceptional scientific achievement. And out there somewhere is an asteroid with his name on it, not Kevin, but Zahnle. 7860 Zahnle is out there somewhere floating around. And he's going to talk about, I'm not quite sure what he's going to talk about. I guess the abstract is about Xenon.
Xenon.
The noble gas Xenon.
That's it.
Yeah. So
okay.
Welcome, Kevin.
Well, thank you for the welcome. Okay, we're going to talk about Xenon. You look excited. I just recycling a first attempt at this talk. This will be, you're my, as I mentioned earlier today, you're my guinea fowl for this talk, and you can squawk if you don't like it. We know of 3 atmospheres of habitable planets. This is the connection with this habitable planet thing that we're all supposed to pronounce correctly, and I got it right that time. But sometimes I say habitable, and then it's wrong. But Earth's current atmosphere is one of our examples of a planet with a habitable planet, an atmosphere of a habitable planet. Another known example is Earth's Proterozoic atmosphere, which has a different composition than the Phanerozoic atmosphere. And the third known atmosphere of a habitable planet would be Earth's Archaean Atmosphere, which has, again, a different composition from the atmosphere today. One of these 3 atmospheres is well characterized. The other 2 are not so much well characterized. The Archaean Atmosphere is the stranger of the 3 because it lacked oxygen. And because it faced the great challenge from the faint sun, Earth's struggle against the faint young sun was much straighter in those days. The battle was pitched over continents and ice. It's widely suspected, or at least desired, that hydrogen or methane or some other interesting gas could serve as a greenhouse gas, something fun like nitrous oxide, something that gives, put a laugh into your day. But of hydrogen and methane, which are the 2 most popular choices as alternative greenhouse gases, of course, there's always CO2, right? So we're never, this is not like the Mars community where CO2 doesn't really work and they have a problem and they have to go and they need the interesting greenhouse gases. We don't really need it. We can get by with CO2. It's the null hypothesis, but it's not cool. And so let's just look at the other ones that are more interesting. A problem with methane is that it's very geologically stealthy. You can imagine that it might create hazes that might fall down slowly as little particles that might accumulate and pollute your shales or something, but it's not actually a very big flux, and it's not a very strong signal, and certainly it hasn't been seen clearly. And hydrogen is, itself is very nearly invisible to the geologic record. About all you have to work with is D to H ratio that may have changed over time. But D to H is not a very stable ratio in geological samples. Diagenesis will tend to change it. And it has not been generally accepted as a trustworthy fossil. So this brings us to Xenon. We're going to talk about a strange messenger that brings us new information from the Archaean of Earth, Xenon, king of the gases, with 9, not not 4, not 5, not 3, but 9 stable isotopes. And the evolution of atmospheric xenon is going to provide us a new window into the composition of the Archaean atmosphere. You wouldn't think at first that it would do that, but it's going to do that, and you're going to see why in a moment. It'll tell us mostly about hydrogen escape from Earth, and it will tell us about how much hydrogen was in the atmosphere of early Earth. Now, to put xenon in context, a few years ago, I went to the interweb, which is the place you find truth, and there I found this view graph of the periodic table of the videos. This was done in February 2011. I'm sure I should update it. But the various elements are labeled according to how many people have hit the video on YouTube. So you can see that the most popular elements are sort of the obvious ones, like mercury or uranium. People are going to be interested in that. Plutonium. For reasons which I don't get, they're not that interested in carbon. I think they're wrong-headed about that. But of course, number one is xenon. Stands out with that bright orange color there on the right. And this is because I had to fix the video. It wasn't right. I had to clean this up because it was missing xenon. So I put in the correct xenon data here. And it's now you can see it's standing out as number 1. It's a noble gas. It's over here on the right of among the other noble gases, krypton, argon, neon, helium. And they're known because, as noble gases, because they're noble. They won't do any chemistry. They won't stoop to that level. So I guess that's what nobility means. They do no work. That's what Spanish mean by nobility. So historically, the people who do no work are nobles. Gases that do no work are noble. But on the metals, there's noble metals too, and they sit in like crowns or something like that, like gold. That's a noble metal. So we'll start with xenon. Atmospheric xenon is mass fractionated and depleted. And we can conclude from this that xenon escape. Here are the data. I like to show it this way because it really illustrates how different xenon looks from one kind of a meteorite or planet to another. On Earth, you have... Is this thing going to shoot? No, this won't do any good at all. Do I have a stick? Oh, yeah. I like sticks. Oh, yeah. Thank you. Oh, it's like a pike, really. There is no substitute for experiment, said Ed Von Teller. Krypton. What I've done here is I've taken krypton-84, and all of these different kinds of materials have been normalized to the isotope krypton-84. And you'll notice that krypton has a little bit of structure. There's a little bit of a slope here. These orange guys are an instantite achondrite, Pesiano, which is currently, as of 2019, the most popular flavor of material, earth building block, basically. If you're going around to see, you want to be fashionable and you say, what is the Earth made of? And you just tell them instantite chondrites, everybody's going to look at you like you're some sort of savant. Mars is here in triangles. Mars is very solar. So now we go over to xenon and we see a lot of structure. Huge amount of structure over here. Carbonaceous chondrites, that's the stuff that people used to make late veneers out of. It's got boodles and boodles of xenon. And since everybody knew that Earth got its volatiles from carbonaceous chondrites, there was a big problem here. It's like, how do you get from here all the way down to Earth? Big problem. They called it the Missing Xenon problem, and they started looking all over Earth for this stuff. They looked in the Antarctic ice sheets. They looked in shales. They were thinking, well, maybe it's hiding out in mud. And it turns out it's not hiding out anywhere. Earth doesn't have it. It's missing. Another case, these guys, instantite achondrites and chondrites, are the new popular stuff to make Earth out of, but you still have to get rid of a lot to get all the way down to Earth. You might notice also that this is quite a distinct slope. It's like a 60% change from 124 up to 136. See it in Mars as well. That's the fractionation pattern. So you're missing the xenon and it's fractionated. We'll repeat that by pointing out these facts. The difference between air and the meteorites is called the missing xenon. This is actually a little bit over the top. This is all non-radiogenic xenon. It's mass fractionated. This is a very steep slope. As I've pointed out at previous lectures, you could ski down this thing. And it's depleted. It's depleted with respect to the carbonaceous chondrites, and it's depleted with respect to the enstatite chondrites. So by factors of 4 to 20, depending on which initial material you wish to work with. So the evidence that xenon escaped is compelling, because what's left in the atmosphere is much reduced, and it's mass fractionated so that the heavier isotopes are more abundant than the light isotopes by a significant amount, roughly 60% across the span of xenon's 9 isotopes. There's other evidence that xenon escaped. It's not just looking at the patterns. There's also a couple other numbers you can put on this. The 129 xenon is a xenon you get from the decay of iodine-129, which is an extinct radionuclide, half-life only of 15.7 million years. This iodine is gone, and it left some xenon behind, but not much. Earth has very little of it. Earth only has 1% of what it should have. 99% has gone missing. There's another kind of xenon that comes from plutonium, one of our favorite elements, as we saw in the video table of the elements. Plutonium has an 81 million year half-life. This is the particular isotope 244 plutonium, of no use for other purposes. You would not use this in your physics package. It would not blow up. Plutonium-244 is a lot like uranium-238. Well, it has one of its decay modes is spontaneous fission. Occasionally, it will spawn xenon isotopes when it spontaneously fissions. And one of those isotopes is xenon-136. And you can count up how much you have in Earth's atmosphere, and it's about 4% of Earth's xenon-136 is from plutonium. And so you find that 80% is missing. And you say, how do you know how much plutonium was on Earth initially? Well, you know the plutonium to uranium ratios that were present in the oldest meteorites in the solar system. So you know what you started with. So by the time you start seeing it in Earth, 80% is gone. So 4 out of 5 of these plutogenic or physiogenic xenons is missing. And again, it has to go somewhere, and it's not inside the Earth. That leaves you escape to space. Now, there's new geological evidence that xenon fractionation didn't just happen at the beginning of history, but it was spread out over 2 billion years. And these are examples of gases trapped in rocks that show you why it looks different. The atmosphere today are these blue boxes. If you ask why is planet Earth blue, well, you already know. There's nothing you can do. Solar is gold. And in between, you find these Archaean samples with slopes that are intermediate between modern atmosphere and solar. So that you see that the Archaean xenon is like half or 3/4 ripened compared to the fully ripe xenon of the modern atmosphere. If you were to plot up the history of this, and Guillaume Avis has done a great job of doing this. He's worked with Bernard Marty and Majuli Pujol to create this compendia. And I plotted them up with colors. Nice blue color for oxygen, because you want to be able to breathe the modern atmosphere, right? And if you're into mass-independent fractionation of sulfur isotopes, I have a gold color over here for that. But what you see is the extent of xenon fractionation has increased monotonically over the history of the Earth. Most of it occurred in the Archaean and the Hadean that precedes the Archaean. Possibly some has occurred after the Archaean in the Neoproterozoic. Possibly not. The data are not as good because the signal is very small. And then it asymptotes to the modern level, somewhere around 1.8 to the present, with no significant change since then. So the fractionation occurred during the first half of Earth's history, and as the fractionation is due to Xenon Escape, presumptively, Xenon escaped through the first half of Earth's history. This is quite a demand because xenon is the heaviest gas in the atmosphere. So you're saying the heaviest gas is escaping to space. You're probably thinking that may mean everything else should escape to space. Is there evidence for that? I just showed you there wasn't. Krypton has not escaped. So it's more complicated than that. In a traditional hydrodynamic escape model, which is what people use to explain xenon escape, a neutral wind of hydrogen is blowing off to space and pushing any gas in the atmosphere with it into space. It's snow plowing out things. And it snow plows according to how massive you are. So xenon's the hardest thing to snow plow out. Krypton's a little easier. Argon's a little easier than that. But you don't see any effect in krypton or in argon. You only see it in xenon. So that was the problem with neutral escape. If neutral xenon's what's escaping, all the gases are going to escape because xenon's the heaviest gas. But there's no evidence that krypton or argon escape. So that leads, you need a mechanism unique to xenon that can also work late through Earth's history, through the Archaean. And that mechanism is that xenon can escape as an ion, which is a unique property to xenon because it's easier to ionize than hydrogen is. The other noble gases are harder to ionize than. I was told not to notice. I did not hear it. I did not notice, as you can tell. Hydrogen ions can escape if there's no magnetic field, or it can escape along open polar field lines that meet out, that leave the Earth through the pole and connect with interplanetary space. And so you have this open path from the pole, so an ion can escape there. Or if there's no magnetic field at all, ions can escape. Now, hydrogen ions, protons, is another name for them, can drag xenon ions to space because the Coulomb force links them together. The Coulomb force is very strong. It's not like two billiard balls hitting each other. The Coulomb force has infinite reach. It's inverse square. So it's like action at a distance. And as the temperature gets lower, the Coulomb force becomes relatively more potent at connecting things because the velocities are smaller at cooler gases. So as the Coulomb force becomes very good at linking hydrogen escape to xenon escape if the xenon is ionized and the hydrogen is at least partially ionized. So that's the hypothesis. And then because the lighter isotopes of xenon will escape more easily than the heavy ones, you leave behind an atmosphere which is depleted in xenon but enriched in the heavier isotopes. This is a cartoon I drew of the picture that I'm imagining, and we will not model this at all because this is too complicated for us. But if we were better modelers and really smart, we could do that. We would have this magnetosphere, this closed part of the magnetosphere in the equator of the Earth in which the hot hydrogens and hot protons are connected and are held in by the magnetic field. Then we have the open field lines, which leave through the poles and which the hydrogen flows freely into interplanetary space and can drag the xenon ions with them. The sun's over here on the right, sends a solar wind in. You got a bow shock. Everybody likes to, a lot of people like to talk about the solar wind and escape, so I mention it here and I put it in the picture. I think solar wind will enhance this escape process a little bit, but I don't think it's a big deal for this problem. We intend to test this, by the way, to look for xenon on the moon that uniquely terrestrial, but it's probably not going to work because people have already looked for terrestrial xenon on the moon, so we're not too hopeful about finding it. The picture looks better on my screen than it does here, by the way. It's got more colors. We've lost some colors here. So step one for modeling, hydrogen escape. I'm going to do a model of hydrogen escape because I need a scaffold on which xenon can escape. So first you have to create an atmosphere of hydrogen escape with protons that are escaping, and then you're going to treat xenon as a trace particle to see whether it can be lifted off along with the hydrogen. The model is very simple. It's got CO2 and hydrogen. That's the entire atmosphere. I've chosen CO2 rather than N2 for the specific reason that CO2 is a good radiator, radiatum coolant. I wanted to include the ability of the atmosphere to cool itself rather than escape. The atmosphere is heated by EUV. Many of you are familiar with the high EUV hypothesis for the early solar system. We've got cooling, as I said. We compute the temperature. We're going to have transonic escape, because that's really cute. It looks really fun to watch those things hit the speed of sound on their way out. I think that's not really important, but it's something that I thought was important and people thought was important, and so you have to include it. But it's probably not really important to the escape problem. It's just important for what the overall flow looks like. So if you were an outside observer and wanted to ask, what is this going to look like, you have to include transonic escape. If your interest is just how fast is hydrogen escaping, how fast is xenon escaping, you don't need to do the transonic thing. The transonic thing is the outer boundary, effectively. It's just saying that the outer boundary does not provide any back pressure, so the escape is free. The method is a shooting method. It's the dumbest of all possible methods and the most American as well. So we're shooting from below the homopause, and the problem with shooting is that this is a stiff system. So there's a limit to how much you can do. But for a simple enough system, shooting will work. So what the shooting is that you iterate the conditions at the bottom and you integrate up. Dead simple stuff. It's the kind of thing that if it works in seconds. If it doesn't work, you get nans in seconds, and you can go back and work on it some more. The approach is assuming the hydrogen flux, and then I solve for the EUV escape. That's easier than assuming the EUV flux and solving for the hydrogen escape. It's much simpler to do it the other way around, beginning with hydrogen. We've left out the magnetohydrodynamics rather than include it. In the future, I've always meant to, for the last, since 1983, when I first started trying to do this problem, I've always poked at the magnetohydrodynamics. But I've known many people who do MHD, and I've noticed that something that links everyone that does MHD simulations, that they're all very depressed. And the reason they do so is that it's not a lot of, you don't get a lot of reward for your simulations. It's just there's too many things that can happen. So I've always, in the end, avoided it. Thermal conduction is another term that's often included in these models. We're going to leave it out because we're not going to need it. We're going to be dealing with EUV fluxes, which are too high for thermal conduction to matter. If you're interested in a stable atmosphere, you absolutely need this. A stable atmosphere requires thermal conduction in order to be stable. Thermal conduction takes heat from the hot thermosphere and brings it down to the lower atmosphere where it can be radiated away. And so it's necessary for a stable atmosphere. A couple of examples of what these atmospheres look like. It's computation here. This is the same figure. On the left, I've got a funny logarithmic axis. It's a logarithm of an altitude above the homopause, effectively. Homopause is the height in the atmosphere where the different gases are equally mixed and above which each assumes its own scale height. On the right-hand axis is linear. This is just linear distance. So the right hand shows you the size of this hydrogen exosphere that's escaping. It's big. It's several Earth radii. It extends up. But all you can see on this plot is H and H plus and temperature and H2. You can't see the structure. So this funny logarithmic scale is here to show you the structure. And the structure that's going to interest us is you got a lower part of this ionosphere with molecular ions, the formal HCO+, which is a popular ion in astrophysics and is a popular ion in this model. And above that, you have protons. The H3+ is a minor species, but a very good infrared radiator, and it actually handles 20% of the energy budget, even though it seems like there's not a lot there. The temperature, as you'll see, is about 1500 at its maximum. So it's not super hot. So this hydrogen wind is flowing off into space. It's not all that hot. And it has a lot of protons. Proton density is around 10 to the 7 or 10 to the 8 in here. So it's quite a lot of ions to couple to the xenon. So comparing our model, I'm going to put this massive thing down. It's getting on my nerves. Stay. Speaking of big, there's this gigantic coffee that I was given by Owen. I have to do something with it. Okay, coffee break over. We're going to go back. We're going to look at the predictions of the model for hydrogen escape. And what I'm comparing this to is, well, this is EUV relative to the modern sun. 100 is a lot. This gets you deep in the Hadean. Archaean is sort of around in here, in the range of 10 or so. And modern Earth is 1. Just to get a perspective on it. The other axis, the y-axis, is the hydrogen escape flux. And I don't have a good intuitive way to describe it yet. We'll get to it. I think it'll become more intuitive as you've seen it a bunch of times. There are 2 limits shown here, 3 limits shown. Energy limited flux. This is a popular limit in the astrophysics literature where they say, oh, let's count all the photons that hydrogen can absorb, and we're going to say that's all going to go into escape. Boom, that's the energy limit. That makes sense. That's the upper limit. And that one is the one in 2. And I've heard there are going to be 2 buzzers, not 3. 2, you shall count the 2. The purple line is if you include far ultraviolet radiation, which is 200 nanometers or short, things that water or CO2 can absorb. And so there's more energy, and it'll be a higher energy limit that you would get from doing that. The other limit, the black limit, is the diffusion limit. And this is where the hydrogens have to move through the CO2, which itself is not allowed to escape. So the CO2 is static. The hydrogens are pushing their way through. They're pushing the CO2s up so that the CO2 is inflated, but it's static. And the H2s are pushing through. And the blues are our calculations. And they show that as you get to high EUV levels, the hydrogen escape asymptotes to the diffusion limit. The diffusion limit is a good limit, but it's an upper limit. The energy limit works better at low. It's more important at low hydrogen escape rates, low EUV. So we did a whole bunch of these at different amounts of hydrogen. So we have hydrogen amounts of 30%, 10%, 3%, 1%, and 0.3% as the mixing ratio in the atmosphere. And these models all asymptote to the diffusion limit at high EUV, which is on the right. And they go parallel to the energy limit at low EUV, although they're well below the energy limit because there's only 1% hydrogen, and most of the EUV is passing through the hydrogen and being absorbed by CO2 at the bottom of the atmosphere. Compare to a Hydra Code model. It's a completely different model by Kuramoto et al., where they use a time-stepping Hydra Code to solve the transonic equation with thermal conduction of hydrogen escape. But they don't have ions, they don't have CO2, except implicitly as a lower boundary condition. And this was very gratifying because we got the same answer they got with a completely different physics, which is normally a pretty good sign that the 2 models they're getting the same answer, they're doing it in different ways. But it does show that we're doing pretty well. But we can cover high amounts of EUV that they cannot do with this Hydra Code. It blows up, presumably, if the EUV is too big. We can cover much more parameter space with our approach. Of course, I call this success. On the other hand, there was another model published in 2005 that got different answers using a Hydra Code. So I personally think this is for these 2 to work out. They may have a battle to the death over it or something. But 2 out of 3 We're going to go with Kuramoto. But I don't know why TN is different. So I'll just leave it to them to work out why one model got a different answer than the other, because the models are supposed to be the same. Kuramoto was attempting to do the same model that TN tried to do. So I don't know what happens here and why they're different. So Xenon Escape, once we've established what the hydrogen escape is, we're going to use it to establish a Xenon escape, and then we're going to put a lower bound on hydrogen in the atmosphere. So in the Xenon escape model, we got a simple photoionization of xenon. That's about all that's going on. Xenon's, it's a noble gas. Its chemistry is not complicated. It can get ionized. The ion can react with H2 to make, well, it can't react with H2, but it can react with an H to make an H+. It can do a few things. It can't do much. The key thing is this charge exchange, the third thing that we found on our own. It turns out that normally charge exchange between two light, a light ion and an atom is very forbidden unless the energy is resonant. With xenon, we found that the charge exchange into the ground state of ionized xenon was not resonant and was not fast. But we noticed, it has been noticed that xenon has a second state. Ionized xenon has a second state. It's split. And the more energetic state of ionized xenon is resonant with H+ charge exchange. So in fact, you can charge exchange between H+ and xenon. So that if xenon were to become neutral and start falling like xenon, which it would, you think about a brick, you're thinking of xenon. But if you can if it hits an H+, it gets reionized. And so then it gets back in the flow again, and doesn't get to run away. So I draw a cartoon with colors. I think colors are always helpful. The colors are representing of temperature and processes. And the concept, back to the concept, I'm going to keep repeating it. We want to get xenon plus up here with the hydrogen, which is on the top of the atmosphere, and you want it to get up there. And once it gets up there, the H pluses heading to space will lift it off with them, if there's enough H+, and if it's leaving fast enough. We're going to call the transition between the upper atmosphere, which is warm, and the lower atmosphere, which is cold, the baropause. So we're coining a word here for heaviness, heavy sphere. So down in here, we got CO2. And the chief ions down here are HCO plus and CO2 plus. And then in the lower atmosphere, it's well mixed. And this atmosphere has only these three components, CO2, H2, and xenon. Implicitly, it has methane, because methane will break down to make these by photochemistry. So methane will not reach this altitude. So the xenon method, again, we have escape. We do the shooting method again. We have an ugly modeling parameter that I'm not going to talk about for want of time, just to say that models often have ugly modeling parameters in them, and we can talk about them. But it's not polite to. We have left out magnetohydrodynamics and so forth. We've left out nitrogen, which will have to come in. In the future, O2 and O+ and water need to go in to a model like this. They're going to be important to us in the future. So the structure of the atmosphere looks like this. Going back to this funny logarithmic axis here. The lower atmosphere, you've got neutrals. There's this intermediate region, about 80 kilometers thick, which is dominated by molecular ions, things like the HCO plus and CO2 plus. And then above that, the dominant ion is H plus, and escape to space is pretty quick from the baropause. So we have, our model has to do three things. It's got to get the xenon from here to here. It's got to ionize the xenon and keep it ionized, and then it's got to take the xenon pluses from here and put them in space. When you get xenon plus up here, it's only the only things that matter are is the hydrogen escape flux. The solar EUV, and the amount of hydrogen in the atmosphere. So that it's a necessary condition for xenon escape that there be enough hydrogen in the atmosphere that from here to space happens. This section is another problem that addresses a different set of physics, but is not related to the amount of hydrogen in the atmosphere or the EUV flux. It's related to other factors. The atmosphere is, the xenon's all ionized. I just wanted to show that. If you look at the fraction of xenon that's ionized in this atmosphere, it's ionized, particularly high up, where it matters to us. It's all ionized. It's like 99% ionized. Finally, got to put some constraints on this. The mass fractionation of xenon is about 4% per atomic mass unit. So that's going to be one of our constraints. And we're going to divide our xenon escape between the Archaean and Hadean roughly equally. The total loss of xenon is coming from plutonium constraint. And the plutonium constraint tells us that xenon is depleted by about a factor of less than 5, because Earth retains 20% of its plutonium fission xenon. So it's less than a factor 5. And this is where we got. This is the model result. And it's gone. The purple is gone. I am so sad. There used to be a purple region right in here, which was the region that is favored. And now you have to imagine this region that is favored. And so we will just imagine it there, just sort of spend a moment imagining this purple region. The left hand, the lower axis is the solar irradiation, this time on a logarithmic scale in units from about 5 up to 100. On the left-hand scale, we have the hydrogen mixing ratio. The preferred solutions are in this region of the plot. And the length of time that it takes to achieve xenon loss and fractionation is indicated for the blue curves. So we're talking some process that takes 100 million years, requires a hydrogen mixing ratio of 10%, and a solar EUV of, say, 30 times the current. That's sort of the sweet spot. But there's a region around there that's good. The whole spicled region of gray, which you can see, which is not invisible to you, are regions where it's possible, that can possibly produce the xenon fractionation that you see on Earth. So the lowest hydrogen mixing ratio that's possible is like 0.8%. So just under a percent. And below that, xenon escape does not occur. Xenon escape, I just said that. How did it know? Xenon escape is possible in the gray zone, or gray, for those who can't spell gray, or aluminium. The purple zone, the purple haze, which you cannot see, still out there. The timescales are how long it takes. I told you that. And the purple haze, which you cannot see. Darn. Let's see if we can see the yellow. Can we see the yellow? Kind of. Okay. That's the ancient solar EUV before, say, 3 billion years ago. So you just barely, the late Archaean just barely falls in the allowed amount of EUV to get xenon fractionation. You're talking a few percent hydrogen to get that. So you have to meet both criteria to get xenon escape. You have to both have enough EUV and you have to have enough hydrogen in the atmosphere. At 3.5 billion years, moves a little to the right, a little higher EUV, moving closer into the sweet spot. The model works much better here, get back to the Hadean. Late Hadean, things work really well. You can see where the purple used to be. See? It's outlined. That's where the purple was. Oh, maybe it'll show up in the next one. as we go back to the beginning of time. Oops, we passed it. Circa 4.4 billion years when the sun was very active. So that's the gist of the model, which is that in order for xenon to escape from Earth, we're requiring a few percent hydrogen in the atmosphere, EUV levels of 10 to 100 times today. And as an example of what this requires, what this means for Earth, assume constant hydrogen through 3. It's different than a buzz, but it's just as surprising. Assume constant hydrogen, and assume that the sun is fading according to a popular power law of the EUV decay. This is going to require that you lose 1 to 2 oceans of hydrogen. So the hydrogen from 1 to 2 oceans of water is lost. That's a requirement. Yet there's very little xenon escape. It doesn't actually produce enough xenon escape. It does produce the fractionation. The escape stopped at 3.5 billion years. It didn't continue on to 2.5 billion years. It didn't last all the way through the Archaean because the Reba's power law doesn't have enough EUV in it at 2.5 billion years. This is an artist's conception of the model. The black line is nothing happening. Hydrogen mixing ratio of 1% throughout. Okay, we'll do example 2. Assume intermittent hydrogen. This is what I like. I don't want hydrogen to be constantly present because if it's constantly present, you're going to lose too much hydrogen from Earth. So we're going to assume intermittent hydrogen. And we're going to let the solar EUV randomly bounce around between high and low values that are consistent with the kinds of values in Rebus et al., but with an envelope picked randomly. The result of this is that xenon escapes only when both the EUV and the F of H2, so only when there's enough EUV and only enough hydrogen in the atmosphere for escape to happen. Escape episodes are brief. They total to only like 30 million years over a billion-year timescale. And the total hydrogen escape depends almost entirely on how much hydrogen escapes when xenon is not escaping, because that 30 million years isn't long enough. This is kind of a cartoon of what I have in mind. And when I say random, this is just a total cartoon to give you a sense of what hydrogen would be doing and when xenon would be escaping. So when the hydrogen is high enough and the EUV is simultaneously high enough, you can get xenon escape. And this is an example where 0.65 oceans get lost in 2 billion years. The red triangles are those few episodes when the hydrogen escape rate is high enough and the high enough for xenon to escape. I don't know how clear this is, but it's just a cartoon. I just made it up, so you don't have to remember it. I did another one that was more extreme with low hydrogen escape to try to really push it down. I could get it down to a quarter ocean in 2 billion years, but the hydrogen mixing ratios in the Archaean would look kind of like this. They'd be bouncing around between 10 to the minus 3 and 10 to the minus 4 with rare excursions above 1% in order to get that kind of a result. So if the hydrogen is more constantly around 1%, you're losing oceans. It's a lot of hydrogen lost. But if the hydrogen is usually rather low and only occasionally has a spike, then you can simultaneously explain the xenon results and keep the hydrogen escape rate low. But this has very different implications for the environment and the atmosphere of the typical Archaean environment, which would not have nearly as much hydrogen in it. But it's just, again, it's just a cartoon. It's an illustration. 2 other constraints. The oxidation constraints on xenon, on hydrogen escape. Cumulative mantle oxidation. Currently, the best number I could find for the amount of ferric iron in the mantle, if all of it's due to oxidation by water, that costs you 1 ocean. So it's not that much iron that's oxidized in the mantle, less than you might think. It's about an ocean's worth. If all the CO2 in the atmosphere came initially from hydrocarbons, so if the carbon of Earth was all accreted as graphite or as tar, you could get 0.3 oceans of water used up to make the CO2 from those hydrocarbons. This is perfectly reasonable. You have to think that the likeliest way Earth accreted its carbon was as a tar. So this is part of the accounting you have to include. So I could come up with about 1.3 oceans of, maximum 1.3 oceans of hydrogen escaping by accommodating that as oxygen in the mantle. But there are other ways to oxidize the mantle than hydrogen escape. You can also oxidize it through the perovskite decomposition at the base of the mantle, where FeO is supposed to go to Fe2O3 plus metallic iron, which goes into the core. That appears to happen in laboratory experiments. So this 1.3 oceans is an upper bound on how much oxidation I'm allowed to do. So we're pushing up against that. We're pretty much using it all. There's another issue, which is the rate of mantle oxidation. I'll talk about that right now. This would be the rate that the mantle takes up the oxygen that the hydrogen escape left behind. So we have water, take the hydrogen from the water, escape at the space. What do we do with the oxygen? We're going to combine it with iron, and we're going to stick it in the mantle. How are we going to get it in the mantle? One method, we're going to oxidize the seafloor and subduct the seafloor. The other method is we're going to oxidize the continents and then erode the continents and take those oxidized pieces and send them down the subduction trench back into the mantle. Those are the two methods that I can think of for doing this. And if you add it up, you get about 0.25 oceans per billion years as a guess. And I have some cartoons of this. Here's my cartoon. I like it because it's got soothing colors. And you can see them all, too. None of the colors are missing on this plot. The concept here is that the mantle is circulating in 1 billion years. And the upper 1% of that mantle is being oxidized as the seafloor. This is kind of on the upper bounds, but that's the 15 times 10 to the 12 moles per year. The 3 is a lower estimate on this from Ozaki et al. They took an estimate of the same thing. How rapidly can you take up oxygen from the surface and put it in the mantle? The continental numbers are taking the continent and tearing it down in 1 billion years and subducting it. That might be actually on the long side for those earlier continents. They may not last as long as 1 billion years, but I picked 1 billion as a nice round number for the earliest continents to be oxidized, eroded, and subducted. And rebuilt too, of course, but rebuilt out of more reduced materials. Biological iron fluxes are bigger, according to Ozaki et al., by a factor of 5 or 10. And these numbers are larger by a factor of 5 or 10. But this is iron that's moving back and forth between oxidized and reduced form before it's been lost to the mantle. So it's a cycle, a biological cycle that they're imagining. And the transient amount of hydrogen that would be in that atmosphere would be 2%. Or as methane, it would be 0.5%. This, though, can't be maintained over 1 billion years because the hydrogen escape rate is too fast for the mantle to take up this oxygen. But within a factor of 2 or 3. It's not a terrible mismatch, but it's a mismatch. And they are good conditions for xenon to escape episodically, which is why I like it. These brief blooms that produce hydrogen-rich atmospheres that last for short times, that's the best fit to the slow, persistent loss of xenon over Earth's history. So why did it stop? Did the sun just get old? And the answer to that is yeah, it did. The EUV got weaker and weaker and weaker, and by 2.5 billion years ago, it was a rare time when the EUV was high enough for xenon escape to occur. Did hydrogen or methane become too rare in the atmosphere after 2.5 billion years? Well, you've switched over to an aerobic atmosphere. You've got oxygen now, so they might have become too rare. So that's a maybe. You might not have had the hydrogen you needed, the 1% hydrogen mixing ratio in the atmosphere you needed for xenon to escape. Or was it the oxygen? And this is another probably. O2 is a problem for xenon escape because O2 will charge exchange with xenon ions. So if you make a xenon ion It finds an O2. The next thing you have is you have an O2 plus ion, which you're going to lose, and a neutral xenon, which will fall. And then your xenon's not escaping. So that's bad for our perspective. With fewer xenon ions, you get less xenon escape. So we have 3 good ways to stop it at 2.5 billion years ago. It's hard for xenon to escape. It's the heaviest gas in the atmosphere. It's not easy. So I think this might be the conclusion. I dare say it is, because I see no more slides. So I can look into the future, and I can see that there are no more slides, and this is your last one. So let's go through the points. Xenon fractionation and depletion can be explained by xenon ions being swept away by a partially ionized hydrogen planetary wind in the early Earth's history. Continuing evolution of xenon isotopes throughout the first 2 billion years of Earth's history, maybe 2.5 even, imply that hydrogen or methane were abundant at times. Not all the time, but often above 1% in the atmosphere. Throughout the Hadean and the Archaean. This has implications for Earth's climate, among other things, because these are greenhouse gases at some level. A loss of an ocean or more of H is plausible, but it's pushing the upper bound. I think 1.3 is my feeling is an upper bound right now for the amount of hydrogen that I would like to see escape, given the oxidation state of the mantle. Hydrogen escape was an important driver of oxygenation of Earth and biases the direction of biological evolution. I never mentioned this, but I think it's important. I think it's important that hydrogen escape is occurring at a considerable level throughout the Archaean and Hadean, and I think it's important that as time goes on, the whole system of evolution, biological evolution, is being biased in the direction of using oxygen, of developing aerobic economies. This would be Catling et al. 2006, in fact, as it gets more and more biased to using oxygen. Eventually, you switch over to the oxygen economy, and as we all know, the oxygen economy is 10 times better than its predecessor. And it allows for things like animals and astronomers and TPFs and things that we all hold dear. But you need to have animals that are able to use oxygen to have that kind of energy available. And you don't have that before you have O2. And in this hypothesis, it's hydrogen that escape that brings that about. And that is, as I said, is the last of the few graphs. And so your time here is over. You're done. Thank you.